Hey folks, this is a quick lecture on reflection. In this video, I'm going to be talking about different boundary behaviors of light, the law of reflection, specifically applied to light, but really applied to all waves. I'm going to talk about the difference between specular and diffuse reflection, and we're going to discuss how additive colors affect the color of light, a little bit about color and why we see what we see. So let's get right into it. Light rays always travel in straight lines. And really all rays do. Rays for any wave do. And we can see that in the image here. These are lasers. They show us the light beams traveling in nice straight lines. They travel in straight lines unless they enter a new medium, they reflect off of a new medium, or they are scattered from particles. And we'll talk about what scattering is a little bit later on. Today, actually let's talk about the three boundary behaviors of light. When electromagnetic waves strike matter, three things can occur. They can be transmitted into the new medium. So this is the process by which incident radiation passes through matter. And when it enters that new medium, of course, there is a change in the wave velocity, and therefore a change in the wavelength, although our frequency stays constant. And this is basically light passing through glass or light passing through water. Our light travels just through our new medium just fine. Absorption is what occurs when the light or the wave energy is, absorbed by the medium. And it's generally going to be absorbed as heat. This is one of the reasons why sunlight heats up the surface of the Earth, because most of that radiation is going to be absorbed, or a lot of that radiation is going to be absorbed as heat. And the third boundary behavior is reflection, in which the radiation hits the boundary and then is bounced off the interface between the two media in the opposite direction. And we're mostly going to be talking about reflection today. So the amount of energy that is transmitted, reflected, and absorbed depends on a lot of things. It depends on the physical properties of the two media. It also depends on the wavelength or frequency of the radiation that's hitting. For example, infrared radiation is absorbed well by the atmosphere, but visible light is transmitted through the atmosphere. And this is one of the reasons why we can see, one of the reasons why we have a greenhouse effect. And the amount also depends on the angle at which the incident radiation strikes a surface. And here are a few diagrams that represent our different boundary behaviors for light. This is the transmission of a ray of light. Our ray enters a new medium, and because it changes speed, it bends, it refracts. And then it also leaves that medium, and it refracts again because it changes speed again. Here's reflection. Our ray bounces off the new medium. Scattering occurs when basically light particles are just kind of scattered in almost random directions. And absorption is what we get when our energy is kind of absorbed as heat into the medium. One thing to note, when an object heats up, it also emits that radiation back as different light. And this is why we can use things like thermal imaging. This is also why we have greenhouse effect and global warming, because the Earth absorbs visible light and emits infrared radiation, which is then absorbed by the atmosphere and re-emitted back down to Earth. Reflection is one of our boundary behaviors, the turning back of a wave at the boundary of a surface. Here are three rays of light shot at a surface and reflected back. The rays that are striking the surface are called incident rays. The rays that bounce off are called reflected rays. Notice for each of these incident and reflected rays, we draw a dotted line that's perpendicular to that surface. It's always at a right angle. This is called the normal. It's called normal because normal means perpendicular. And we're going to be using the normal all the time when we're working in optics to measure angles. Whenever an incident ray strikes a boundary, the reflected ray always reflects at the same angle that the incident ray hit. So we would say the angle of incidence, theta I, is equal to the angle of reflection, theta r. In mathematical form, theta I equals theta r. We measure both the angle of incidence, theta I, and theta r from the normal. So this is our theta I, and this is our theta r. By the law of reflection, those angles always have to be the same. And here's our normal. I'm going to try and draw it as our dotted line. Normal. Always perpendicular to the surface. There are two types of reflection. The first is specular reflection, which is what we get when you look in a mirror. And that is what happens when all of the incident radiation coming from one direction bounces off in one direction as well. And it's really just what happens when waves reflect off of a very smooth surface. And really it's just that the surface is pretty smooth compared to the wavelength of our incident radiation. So visible light has a wavelength of about 5 to 700 nanometers, give or take. And so in order to get smooth specular reflection of visible light, we have to have a really smooth mirrored surface that's smooth to about 500 or 400 nanometers. There aren't many bumps on that smooth glass surface. So this is specular reflection. Here's another example of specular reflection. These are radio satellite dishes. Now, they may not look smooth to us, but because radio waves have such a long wavelength, they're actually smooth compared to a radio wave. So they reflect radio waves perfectly as they come down, and they reflect all those radio waves into this focal point, this receiver in the middle. Obviously, we can see through them because they're not smooth compared to the size of visible light. The other type of reflection is diffuse reflection. I'm going to just cross off scattering for now. We'll come back to that later. Let's just stick with diffuse reflection. Diffuse reflection is what happens when our incident radiation hits a surface and it goes kind of in random directions. It's unpredictable which way it's going to reflect. And diffuse reflection happens when the surfaces are rough relative to the wavelength of the light, relative to the wavelength of the wave. Most surfaces are pretty rough compared to the wavelength of visible light, which again is something like 400 to 750-ish nanometers, very small. So light kind of scatters in random directions. Now keep in mind that this light is still obeying the law of reflection. It's still scattering off of the surface at the angle that it hits. It's just that because the surface is so rough, in slightly different places we'll get very different angles of incidence and angles of reflection. So it kind of goes in all directions. Most of what we see is from diffuse reflection because surfaces are rough compared to the size of visible light. For example, this apple, we're shining white light on the apple. Most of the light is absorbed except red light, which is reflected diffusely in all directions. Some of it goes into our eye, and the stuff that goes into our eye is what we see. So the colors we see come from the colors of light that enter our eye. We actually have 3 different cells in our eye that absorb different colors of light. One that absorbs mostly red, one that absorbs mostly blue, and one that absorbs mostly green. And if we have light of all different colors, we combine them and we see white light. So white is a combination of red, green, and blue. And we can get different colors by adding different combinations of red, green, and blue. We call red, green, and blue the primary colors of light for this reason. We can actually get any color by combining red, green, and blue light in different ways. Magenta, yellow, and cyan are what we get from combining just 2 of the 3 colors. When we think about objects, though, objects aren't made of light, they're made of pigments, and each different object is going to absorb light differently. What we see are the reflected colors, which means that an object is going to be absorbing all of the other colors. For example, if we have a red apple, this is my apple, and it's red. If we shine white light on it, then that means it's going to absorb the blue. I'm just going to do big B for blue, and it's going to absorb the green, which means it's only going to reflect the red. So our primary colors of pigments are actually different from our primary colors of light. Our primary colors of pigments are cyan, yellow, and magenta based on the colors that they absorb. Magenta absorbs green, yellow absorbs blue, and cyan absorbs red. So here up at the top we have an image illuminated with 3 different colors of light, red, yellow, and blue. And this is the original image. If we illuminate it with red, we can see most of it. If we illuminate it with yellow or blue, we can't see all the details because some of the colors are not going to be reflected or are going to be reflected the same way. The question is, why do tennis players wear white? So we can answer this question in terms of absorption and reflection of light. If we're seeing white, then that means we're seeing all different colors of light reflected. So if you're wearing white, then most of the colors are going to be reflected, which means no colors are absorbed, or very little light is absorbed. Well, the less light that's absorbed, the less energy is going to be converted to heat. So tennis players are going to wear white to keep themselves cool, essentially. The last behavior of light is called scattering. I mentioned it earlier. And scattering is what happens when a photon, an individual particle of light, interacts with an atom. So we have electromagnetic energy that is absorbed by electrons in an atom, and then it's re-emitted in all directions. So it doesn't necessarily obey the law of reflection. The light is absorbed by the atom holds on to it for a bit, and then it re-emits it somewhere else. This is called scattering. It's not really predictable which way it will go. It doesn't quite obey the law of reflection either, and it's just launched in random directions. This is actually one of the reasons that, or the main reason that the sky is blue. When the sun shines white light on the atmosphere, let's say this is our atmosphere. When the sun shines white light on our atmosphere, different colors are scattered differently. I keep pressing the forward button. And blue is scattered a lot more than other colors. So if we look at light that goes off in all kinds of different directions, blue light is going to get bounced back towards the earth in all kinds of random directions. So when we look in the sky, we're going to see a lot more blue than other colors. Since red light is scattered less, more red light is going to just travel straight through the atmosphere towards us. So when we look up at the sun, it's going to appear more red or yellow than the rest of the sky. Also, blue light is going to be scattered away when we look directly up at the sun. Blue. This is a pretty poor drawing because it's, well, my ink color is red. Unfortunately, I can't show how the colors mix. But basically, that's why the sun looks yellow, because blue light is scattered away, and that's why the rest of the sky looks blue, because blue light is scattered towards us from all over the sky. It's also why sunsets look red and sunsets look yellow, because a lot of the blue light is then scattered away before it reaches us. For example, we're over here. Most of the blue light will already be scattered away before it reaches us, and so we'll see more red. In summary, light can be absorbed, reflected, transmitted, or scattered. The law of reflection says the angle of incidence equals the angle of reflection, and we always measure angles from the normal to the surface, which means perpendicular. We should be able to distinguish between specular, which is like a mirror, and diffuse reflection, which is just reflection of light in all random directions. And we should identify how white light is made of a mix of all different colors of light. And that's that. Hope that was helpful. Bye.